All right, we are going to continue our probability lessons. We are in the notes packet. We finished on page 3 last. We are starting here on page 4, and I have great news for you on page 4. We are basically going to not do anything on page 4 this year. All of these symbols notation we're not going to really go into, but we are going to then start on page N5, notes packet, page 5. A big part about doing probability when you're dealing with outcomes of an event, if you really think about what we've covered with our permutations and combinations, it's that you are looking for the number of possibilities of an event happening. Well, we can also think about this as different outcomes of an event and how often outcomes occur. So Venn diagrams, not the ones you only use in your English or history classes, but Venn diagrams in general have a lot of math purpose to them. We can use Venn diagrams to show what's called the union or the intersection of events. And these pictures are in black and white, so they don't tell all the story. But when we're going to start here by looking at basically, there is always going to be some sort of sample space. So we're looking at outcomes of events, just like permutations, combinations, Venn diagrams, you'll see, we'll do examples, can help us with outcomes of events. So we start off in math class Venn diagrams with a big box. There's a box around all of these with a big capital U. The U stands for the universe of all outcomes possible. And then in that, we will have sets of outcomes. And your typical Venn diagram has a left, a right, and an overlap. If it's not in the left, not in the right, not in the overlap, it can still fall in the universe. But we're going to start off with some simple words of union and intersection. You may have seen them before in other math classes. For union, I want you to think about the word unite. Unite, which typically means to bring everyone together. You unite everyone. United States, we bring all the states and unite them to form a country. So when you think of union of sets, we are thinking about everything in the left set, everything in the right set, that all makes up the union. So the union, as is highlighted, is actually everything in a possible outcome is in the union of those two outcomes. Everything. So if I say left only, that's in the union. Right group only, that's in the union. Overlap is in the union. So they use sets A and B. A union B is the same as saying A or B. That's the union. Because if I made set a senior, if I made set B a person that goes to PHS, then you could be a person in, and we'll pick this side A, this side B. You can be, think about all these people out there, right? All the people in the world. We have a group A of seniors in high school. We have a group B of members of PHS. We have a lot of people that are in none of that. That's why we have a universe. But there are people who are seniors at PHS. But if I said, are you a senior or go to PHS, senior or go to PHS, if you're just one of them, you would answer yes. If you're just the other one, you would answer yes. If someone said to you, are you a senior or go to PHS, and you were both, you would still answer yes. That's why the union unites everyone, and it answers the question of A or B. Intersection is just what you think. This one's a lot more obvious. It is just the overlap. So if I left the same groups as a senior is A, a PHS person is B, the only people in the intersection, which means overlap, this is the overlap, would be the people that are a senior and go to PHS. So, bigger picture, if you are in the overlap, are you in the union? Yes. So this is a more specific group because this group, this red space, is part of the blue space, but it's more specific. It's both. This can be A, B, or both. This can just be both. We're going to see this way more when we do examples. It'll make so much more sense. So if there is this overlap, if this overlap is something that exists, imagine if there was no senior at PHS. None of those existed. We get this word called disjoint. Sometimes two circles can be completely separate, meaning just there's no overlap. Nothing's overlap. The reason we teach these three situations is because of probability. When we're working with the addition principle, it's important to know how this works, because if you think about, we have n of a, meaning the number of elements in A. So we have all of the things that are in set A. We have all of these things in set B. If I was worried about what is the union of them, we have to think about this very carefully. So we're going to make the same sets. We have set A. We have set B. And this is the addition principle of probability. What it says is, let's set A, we're going to do this with an example, be the set of business majors registered for a class. Okay, so think of all of this people in this circle would be business majors registered for a class. There's always a universal set that just goes around it. Set B is the students present today in class. Okay. First, we think about, now this is upside down U is intersection, regular U is union. A union B is the set of business majors present today or present today. Because let's think about this. A union B. If you are a business major registered for the class, you're over here. If you went to class today, you're over here. There are people who did both. This both section is the overlap. The harder one to explain is this union, A union B, meaning if you're a business major or you're present today. And I point it out because of the formula, which says you take the number of people in A. So let's say the A circle, this whole circle, this whole thing is 12 people. This whole B circle is 9 people, but 6 people went to class today, right? 6 people went to class. What happens is you get this 6 people, they get counted twice because they are a member of the 9 people in total who went to class today, and they are a member of this group of people who were registered for the class. This is going to be a lot better when we do more examples, but I just wanted to start by saying we are going to have these principles that we are going to do. When we get to the next page, you'll see why it's so important. Disjoint, so basically like saying if I have these Venn diagrams, and nothing is in the overlap, there's nothing there, you don't have to do this step of subtracting the overlap. You don't have to do that step. Nobody is counted twice. That's essentially what this whole slide is saying, is if someone is counted twice, like in this Venn diagram where there is an overlap, you have to subtract them once to get the right amount of people. Let's move on and make it a lot easier. Okay. Here we go. A practical problem. Okay, a practical problem. What it's saying here is U is the universe in a class of 40 people. So this entire problem has total of 40 people in it. A will be the group of students that own a car. Okay, they'll be the own a car group. B will be the students that own a computer. B will be the students that own a computer. Great, they're here. If 30 students own a car, then this entire A circle is made up of 30 people. If 20 people own a computer, then this entire B circle is made up of 20 people. Right away, I hope you can see that we have an issue. There are only 40 people in the class, and if I put a 30 over here and a 20 over there, I have a lot more than 40. I also know that 15 people own both. So the rule that I just tried to show you for when things do overlap, it says take the number in set A, add it to the number in set B, and then you have to subtract the number in the overlap once. Why is that? Because the number of people that own a car is 30. The number of people that own a computer is 20. There's 15 people that are in this 30 and 15 people that are in this 20. So I need to subtract 15 once so that they're still counted one time. So 30 plus 20 minus 15 gives me that 35, 30 and 20 minus 15, give me that 35 total people are in this group. So I want to show you how to properly fill out this Venn diagram now, so you don't ever get confused. And you really don't need to use the formula. Let's take away this 30. Let's take away this 20. And I'm going to show you how to do this problem way easier, because all of those formulas aren't that great. Let's start like this. Okay, 40 people are in the universe. So my total will be 40. Okay. 30 own a car. That's this huge circle. 20 own a computer. That's this whole circle. 15 own both. So I'm going to start with the most specific. And the center, 15, is the most specific. Okay. If set A, right here, set A, has a total of 30, and 15 of them are here, how many more will make up the whole circle? 15 more, because 15 and 15 make the 30. Well, if 15 are here, how many more will just make up the whole circle? 15 and 5 more make the total of 20. And if my universe has 40, and 15, 15, and 5 are accounted for, that's a total of 35, well then 5 of them have neither. They don't fall into that category. And look at this. Using this complex formula that you don't really need would have totaled 35, and then 40 take away 35 would have left us with neither, and it's another way of getting 5. Essentially, to sum it up, when filling a Venn diagram, you have to remember that 30 represents the whole circle. So if 15 are here, then 15 can only be here. And if 20 is this whole circle, and 15 are already here, there's only room for 5 more. And if 40 is the whole box, then there's only room for 5 more. So I want to tell you more like, what is this 5? This 5 would be a people in group B. So they own a computer, but they are not in A. So 5 people own a computer and no car. It's about where you are in the world. That's what these Venn diagrams help us do. Before we move on to probability and odds, I think it's great if we did one more example. And I'm picking this one from your homework packet. This is, I'll write it out. This is homework packet, page 2. Homework, page 2, number 5. And this one has 3 circles. I wanted to step up the game. Let's just do it. Watch. If you always think work on the inside first, you will always set yourself up for success. Here we go. In a survey of 60 people, it was found that 25 read Newsweek. So this whole circle is 25. 26 read Time. This whole circle is 26. 23 use Fortune. Whole circle. 9 read both Newsweek and Forbes. 11 read Newsweek and Time. 8 read Time and Forbes. 3 read all 3. This is where you start. You start with the middle. 3 goes in that middle. Because now you have to think those 3 are already part of every other piece of these circles. So you can't count someone twice. What does that mean? It means if 8 read Time and Fortune, well, Time overlaps with Fortune, this big space. 3 people are already in that space. There is only room for 5 more to make the total of 8. So don't count people twice. And 11 read Newsweek and Time. Well, that's this whole space. And 3 of them are already in the Newsweek and Time place. So 11 take away 3 leaves me with 8. And if 9 read Newsweek and Forbes, but 3 of them are already in the center, they are in all 3. So yes, if someone is in the center, do they read Newsweek and Forbes? They sure do. So don't count them again. So there's only room for 6 more. And now you finish with the outer circles. So if 60 read Newsweek, 25 read Newsweek, 25, take away 8, take away 6, take away 3, leaves me with 11, 17, 18, 19, 20, 8. Leaves me with just 8. And then Fortune on the bottom is 23. Well, 23, take away 6, 5, 11, 14, take away 14, leaves me with 9. And Time had a total of 26. 26, take away 8, take away 3, take away 5, because they are already in the Time circle. Everyone can only go one place, leaves me with 10. And now let's answer the question. Is a Venn diagram Newsweek, Time, and fill it out. We did that. Part B. Fill in the number of people who read only Newsweek. So now we can get very specific once your Venn diagram is filled out. Only Newsweek is, it's just 8, because I filled out the Venn diagram properly. Only Time is 10. Only Fortune, so you can't be here, you can't be here, you can't be here, you could be here, 9. Number 4, Newsweek and Time, but not Fortune. So what does that mean to us? It means you read Newsweek, you're in this circle, but you can't be in this triple overlap. So it's just 8. Oops, sorry, bad color. So it's just 8. Number 4, only one of the magazines. Well, that could be here, here, or here. They all read one of them. So that's 19, 27. That's 27 in total. And now the last part of this that we never filled in was the no magazines. None of them. Well, 60 people in total. And we need to get rid of all of those numbers. So you have to take away 10, 8, 8, 6, 3, 5, and 9. And you will be left with only 11 left. So our last question, the answer is 11. This was our little insight into Venn diagrams. Again, moral of the story is, please only count someone once and work your way from inside out, and we're going to practice these next class. The second part of our notes today is to go over probability and odds. If you've noticed, we have not done a probability question yet together. We've only been doing counting. What is the difference between counting and probability? Well, probability is successes divided by a total, or failures divided by a total. A probability, again, probability can only be a number between 0 and 1. That's a great thing. So if the question ever says find a probability and you ever get an answer that is not between 0 and 1, you know for sure it is time to look at your work because something is not adding up. So, moving forward. If an event can succeed, we're working right here, if an event can succeed in n ways and fail in f ways, what is the probability, we say p, of a success and a probability of a failure? Well, let's take a look. Well, let's use the facts that we have right here. All probability must sum up to 1. Okay, all the probabilities of every event. So it's a measure of chance will occur. The set of all outcomes is the sample space. All the sample space together is equal to 1, meaning all the probability is equal to 1. The ratio in a probability is the number of successes over the total sample space. So what this example uses is a deck of cards. What is the probability of getting exactly one card you want? And then what is the probability of getting the card you don't want? Is just 1 minus the successes. Probability, to sum it up, simplify it, is just a ratio of successes over total outcomes. Most of this stuff in theory talk isn't all that easy to understand, but when we get to an example, it's much easier. So we're going to do a couple examples with probability, and then we will circle back to odds in a minute. So, probability questions. Examples. Let's have it make some sense. Okay. A bag contains 5 yellow, 6 blue, and 4 white marbles. So 5, 6, and 4 makes a total of 15 marbles. That is what's called the sample space. It is all of the outcomes. Our first question says, what is the probability that a marble selected at random will be yellow? So to do probability questions, it's no longer just making counts. A probability question says, how many successes are there? Well, this is a pretty simple one. There's 5 successes. You divide by a total. What is the total? 15 marbles in the bag. So the probability here is going to be 1/3. You could also write this as 0.33. You could also write this as 33%. Probability questions can be fractions, decimals, or percents. Okay, next one. What is the probability that a marble selected at random will not be white? Well, let's do this 2 different ways. We can say it's going to be 1 minus the probability of a white, because to do a not probability, just do 1 minus the actual probability. So 1 minus 4 out of 15. What does that leave me with? 11 out of 15. This is a simple one. So to say not white could also have been, oh, it's going to be yellow, which is 5 out of 15, or, which in probability means add, we looked at that earlier today, add, or blue, 5 plus 6 out of 15 for a total of 11 out of 15. However your brain thinks about this problem is fine with me. Now, we are going to realize that probability gets a lot more complicated. Let's take a look at example 2, which we have to talk about odds first. Odds is just a different way of doing probability. So I'm going to make very simple. Probability is equal to successes over total. Odds, which is right here, it says the odds of a successful outcome in an event is the ratio. So odds is still a ratio, but it is successes not divided by total. It's successes divided by failures. So that's two big differences, odds and probability. They look very similar. Okay, let's do number 2. Okay, 12 male and 16 female students have been selected as equal qualifiers for 6 college scholarships. If the awarded recipients are to be chosen at random, what are the odds? This is an odds question. This is not probability. What are the odds that 3 will be male and 3 will be female? So what we need to do is we need to calculate the ways of getting our 3 males. We need to calculate the way of getting our 3 females. And then we need to see what our total is also. So let's get into it. This is a tough one. So stick with me. I'm going to make more space. Okay. We're going to divide and conquer. What do we have to do? We need to do odds in the end. But for now, we'll start with just how we can do 3 males. So I have a total of 12 males. So I have 12 males. 3 of them are going to get scholarships. How do I choose 3 males from 12 to make a group 12C3? Yes, we're going to use combinations and permutations still. 3 need to be female. So I have 16 females. I need to choose a group of 3. In probability, we said, what does and mean? Basic counting principle said and said to multiply. We are building on the stuff from the first video. So my ways of choosing a success are 12C3 times 16C3, which is 220 times 560, which equals 123,200. Now I need to know how many total ways I can make the group of 6 happen. Well, a group of 6 from 16 and 12 is 12 and 16 make 28. I need to choose 6. What I'm getting right now is called my total, the total ways of doing something. We need the total before we can go straight to failures. So 28 choose 6 is going to be 376,740. If this were a probability question, it would just be this divided by that, and it would be over. But since it's odds, I need to get my failures, meaning all the groups of 6 that are not 3 male and 3 female. The way to do that is take all of the groupings, 740, which are all the groups of 6, and subtract the successes, 123,200 successful groups. What does that leave me with? It leaves me with basically the denominator for an odds question, which is the failures here, which is 253,540. So to answer the question, we need a ratio of successes over failures, which in this case is 123,200 divided by 253,540. That does simplify, if you want, to 880 successes per 1,811 failures. That would be odds. This is an odds question. The only reason it became odds is because we took the total, subtracted the successes to get failures as the denominator. So you have to be very careful if the question says odds, probability, or just total count. Okay, pause this one, take it all in if you need. I'm going to go to our last question of the day. The last question of the day says, a circuit board with 20 computer chips contains 4 that are defective. If 3 chips are selected at random, what is the probability? So probability now is, again, successful outcomes that we need over total outcomes possible. That all 3 chips are defective. So let's think about what it is we are doing. Our event that is taking place is 3 chips are selected at random. 3 chips are selected at random. We need to know the probability that all 3 are defective. So what we need to do is think about the fact that it's easier to start with the total. We have 20 chips on this computer board. We are selecting 3. So what are the total ways of selecting 3 chips from 20? It's a combination. 20 chips in total. I'm thinking about all the groups of size 3. So that is my total. How do I get my successes? Well, what is this? What is a success in this? A success would be if I select 3, if I choose 3, and all of them are defective, which means how many defective are there? 4. So I need to think about all of the ways I can get 3 defective chips from 20. Okay, well, the only ways to get 3 defective chips is if I make groupings of 3 from 4 total defective out of 3 from a total of 20. This is 1 over 285. And now I might blow your brain, but I'm going to think about this question in a totally different way. Let's think about this the way we thought about how we made our ID numbers the other day. And it said that a computer board has 20 chips, 4 of them are defective, 3 chips are selected at random. Okay, when we did our ID numbers, I said, okay, let's make 3 spots because I'm selecting 3 chips. And let's think about the ways of selecting defective chips. Well, if I pulled a chip from 20 and it had to be defective, then I have a 4 out of 20 chance of pulling a defective chip. And let's say this happens. It was a success, because that's how you think, that's how probability works. Things are successes. How many chips are left on the board? 19 chips. How many of those 19 are defective? 3, because I only care about successes. And then after I do that twice, what happens if I go one more time? I have 2 defective chips out of 18 left on the board. Well, do I want each of these things to happen? Yeah, they all have to happen. So this and that, and, which means multiply, that. And if you do that math, it is the exact same thing, because we will learn and continue to practice that combinations and doing your probability this way, where you just think about event and event and event, are really all the same. This is where we're going to stop today. We're going to go to class. We are going to practice all of these concepts as a group. This is some tough stuff, but the video is finished, so your notes are done right here, and I will see you in your next class.